Welcome to our first lab of the semester. What I want to do here is that I want to verbally talk about what we want to do. Today, we want to build a constant volume thermometer. That is, by keeping a volume of air constant, we essentially set up an isochoric process. So that means then that the pressure and temperature have to adjust themselves to keep that volume constant. So we want two measurements. We want a measurement of the pressure and the temperature. And from that, we want to plot pressure versus temperature and predict two quantities, the absolute value temperature value and the universal gas constant. These measurements are going to be rough. And the reason why they're going to be rough here is that we're only using three measurements, and those three measurements of the water temperature, which will give us three measurements of the pressure, is only coming from the tap water. So that means here, the way I did it is I started with the coldest tap water that I could get, which was about 18 degrees C. And then I went to the hottest temperature of the tap water, and I found out it was around 60 degrees C. And then I picked a third value that was in between those two, warm water. Now, when I say warm water, that means what's warm to you? You know it's got to be somewhere in between 60 and 20 degrees C. So you're going to find out that one of the most challenging things to do is to actually measure the pressure. And it would be helpful if you have a second person, but I'm assuming that you will not have that. So what you have to do here is that you're going to have to tape one of the open ends of the tubing to the wall to act as a second person. So let's go in, and I'm going to do a share to start sharing my screen. So here we go. So in this lab here, I want to give you sort of like the theoretical basis of what's actually happening. So here we are. So I want to start talking about the theory to show you where we're headed here. So a basic prediction of the ideal gas law goes something like this. This is only true if we write this in Kelvin. But if we convert this into Celsius, then it's going to be NR, and then this is going to be degrees Celsius plus 273. Now, if I rearrange this, I'm going to rearrange it so it reads pressure is going to then be NR divided by V times the temperature plus a combination of NR divided by V times 273. This is what we're after here. And what we want to do here is that we essentially want to set this up as a line where we now have a slope given by this quantity right here, and we have an intercept given by this quantity right here. We want to use this to plot in Google Sheets or Excel this line here. So now what we want to do here is that, we want to now plot P in kilopascals versus T in degrees Celsius. And what are you going to find here? What you're going to find here is that you're going to get a curve that looks like this. So this is, again, we want to measure in kilopascals. If you don't measure in kilopascals, it turns out that your line in Sheets or Excel is going to be terrible. And what we'll do here is that if we plot this thing, we're going to get a line that looks something like this. And so this line right here, we're going to get from Google Sheets or Excel is then going to be a linear line. And this is assuming that constant volume occurs. And this point here, the accepted value of absolute zero is minus 273 degrees Celsius. Now, when we do this, what you're going to find out here is that this only works if the enclosed gas, in this case it's air, is confined to a volume that does not change. Okay? So this assumes that the volume of air does not change. From this, we can make two predictions. So the first one says this: classical physics claims that all motion stops at the absolute absolute zero temperature value. And the reason why all motion stops here, they're saying that it gets so cold that there's no more molecular motion. So they say here is that then P is equal to zero since no molecular motion occurs. So when I look at this, I'm going to see that P is going to be equal to zero. And what we're going to do here is that we're going to extrapolate to that. And again, this just tells us you stop all motion of atoms. And so you can now see that I'm going to have my line that looks like this. So now I could do a simple calculation that shows you that T absolute, in theory, should be negative of the intercept divided by the slope. That's what this is claiming right here. So that's one of our predictions from this line, where T absolute accepted is minus 273 degrees Celsius. That's what we want to compare this to. The second thing that we do here is that by measuring the slope of the line, one predicts that if I look at the slope here, and I go back up to here where we've defined it right here, you could see that the slope here is equal to NV times R theory. So again, we can then predict this here by having our slope measurement divided by the value N divided by V here. Where we know that the accepted value of the gas constant is equal to 8.31 joules per mole Kelvin. That's what we need to do right there. And what you're going to see here is that we will need to estimate N over V using your local pressure and temperature. And we'll talk about that later. So what we're going to do here is that in order to do this, I already said here that we're going to create a constant volume temperature thermometer to plot pressure versus volumes. Now, what you're going to see here is that our measurements will be rough. And what I mean by that is that their values are going to be in the ballpark, but I would not expect you to get really good values. And the question is, why? Our temperature measurement of tap water are very close in value. So what I mean by that, you're going to set up a table. So you're going to have tap water. We're going to set up a temperature in degrees Celsius. We're going to set up pressure in kilopascals. And the way we're going to get our measurements is we're going to do it like this here. I'm going to take my tap water and I'm going to get it to the coldest value possible. It was around 20 degrees Celsius for me, a little bit below it. And then I'm going to take my tap water and I'm going to try to get the hottest possible value. Mine was between 60 to 65 degrees Celsius. And then we're going to get some value in between that feels warm to you. So now if you go and you look at the curve that we're talking about, so if I plot this thing, what am I actually seeing here? Well, the range of temperature values are quite big, right? This guy is minus 273 degrees Celsius. And right here, because we're talking about water, that value has to be 100 degrees C. What we're going to do here is that we're going to pick three values that are relatively close together. So right here, you're going to see here is that there are three values in the range of 20 degrees C to about 60 degrees C. So you can see that over a 300 degrees, almost 400 degrees Celsius, we're trying to extrapolate and get that line only from a range of about 40 degrees Celsius. So that's what makes it really rough right there. Okay, let's keep moving on here. So now what we want to do here is that we want to build a constant volume thermometer. So here we go. So what you're going to have to do here is that we're going to take the stuff from your lab kit, and here's really the bulk of what you need for the lab. There's some other things, but not very much. Of course, we have a thermometer. We have a little metal canister. We have a white plastic barb that has a thin and thick opening. We have a stopper, and we have tubing. So this is all in your lab kit right here. So now what I want to do here is that I want to show you the overall picture. I want to draw the overall picture. So here's the overall picture of what we want to do. So the first thing that you're going to do here is that you're going to create a stop. You're going to connect the stopper and the tubing with the barb. So you're going to have a black stopper, and then you're going to have a barb here. So that means there's going to be a thin end. Oops. And you're going to connect the thin end to the tubing, and then you're going to connect the thick end to the stopper. So what you're going to see here is that we're going to have a situation where we're going to take our tubing, and eventually this is what we want to do. So this turns out to be our first step right there. Now what we're going to do here is that we're going to insert the stopper into a cup of dyed water. In my case, I had green dye. You don't have to do this, but as an old man like me, I have a hard time seeing. And you're going to see here is that there's going to be a boundary right here. This is the boundary between air and the dyed water. Once I get all of the bubbles out, what I'm going to do here is that I'm going to take a little piece of tape, and I'm going to tape this guy right here, okay? And what this tape does is it just shows that boundary between the air and the water. And you're going to see here, so maybe I should call this a tape marker. Now what I'm going to do here is that I'm going to shove the stopper into a container of water. So when you look at this thing, you're going to have in your kit, we've included this guy right here is a white cup. Well, actually, I want to draw this a little bit better. So it actually looks something. Oh, I made a mistake. I have to force it into the canister, which I neglected to actually mention right here. So here's your canister. So when you stuff that stopper into the canister, you now have this volume of air. So this here is the trapped air. And that's where we get our constant volume from right there. It's that air that does that. Now what I'm going to do here is that now I put it into the cup. So I want to submerge the canister into a water bath. So now you're going to see that I'm going to have something like this. There's the white cup, and the white cup is the water bath. And so when I look at this water bath, that's where I'm going to be putting in my coldest water, my warm water, and then my hottest water from the tap. So now here is the trickiest part. So what you're seeing here is that right here, you're seeing that the tubing is open to the atmosphere. And so now the next thing that you want to do here is that you have a tape measure. And then this is going to be the tape measure. Let's color this guy. And what I'm going to do here is that you want to take this and you want to tape this to the wall so it frees up one of your hands. So now what we're doing here is that we're going to measure from where the red tape is at to the top of the column of water. This height change right here is called delta Y. So when you're looking at this thing, we're going to have some scale. Maybe this reads, I don't know, 40 centimeters. That's going to be 50, 60 centimeters. That's going to be 80 centimeters. Maybe the water goes up to, 80 centimeters or something like that. So by measuring that height, we're going to measure the pressure of this thing. One thing I forgot to label here, this guy is my green dyed water. So does it have to be green? Of course not. But that's effectively what we're trying to do. This is the setup that we want to use here. So here we go. Now what I'm going to do here is that I'm going to go through the details step by step to make sure that you start to do this. So here I go. So now I'm going to do the first step. So the details. So here's step one. We're going to connect tubing and stopper together. So here's what you got to do. I'm going to see this in two steps here. So the first step that I would say is that you want to insert the smaller end of the barb. What is the barb? Look at the barb. There's the barb right there. Take that smaller end and insert it into the tubing. Now, this can be challenging. I'll tell you that right now. I had a hard time doing it. So as a hint to make it slide a little bit easier, I used a tiny amount of olive oil. A little bit of soap will make it easier just to push it in. And then the next thing that you want to do here is that now you want to connect the stopper to the larger end of the barb. So when I look at my picture, here's what I'm seeing here. I have my barb, and you're going to see that it's nice and thin, and then it kicks out and it's fat. Okay, so then you're going to shove this into the stopper, right? So here's my stopper. Ooh. And then my tubing is like this. So this is what you want to do right there, right? This is my stopper. Here is my barb. And then you're going to see here is that now I'm finding that this is now my tubing right here. So now let's go to the next step here. So now I'm at step 2. I'm going to add dyed water into the tubing. I would say that this one is one of the tougher ones. And the reason why it's tough is getting the bubbles out. So let's go through the process here. So what you're going to do here is that you're going to do this here. I'm going to take my tubing, and then it's connected to my stopper. I think I'm not going to want that. I think I'm going to make this so that it stops right there. So you're seeing here is that this guy is my stopper. Now what I'm going to do here is that I'm going to take some type of glass or cup, and then I put in dyed water. Now I wouldn't make it a full cup. I ended up doing about half a cup. So you're seeing here is that this is my stopper. This is my dyed water, and this is my tubing. Now I'm going to move this a little bit down here. And this is my tubing. Now here's what you got to do here. To get the water into the tubing here, what you have to do here is that you have to suck the dyed water into the tubing. That's how you're going to get it in there. Now, I'll be honest, the first time I did this, it tasted like plastic. So if you don't want that, take a Q-tip and some alcohol or whatever, clean out the tube. You'll see that it won't taste like that plastic, but it definitely tastes like plastic. So here I go. So what did I do? So make, let's say, half a cup of dyed water. I used green. Do you have to use dye? No, it's not necessary. But the dye water makes the measurement process much easier. Then you want to drop the stopper into the dyed water. Then you're going to suck on the open end to draw in water. Now, what you're going to find here is that this now becomes important. Only draw in about 1/3 the length of the tube. Don't do too much. You'll see if you do that, it's going to cost you. So now here's what you're finding here. This is the challenge. Getting rid of the bubbles in the dyed water. Okay. So there's a couple of hints. Okay. And you can only do the best that you can do. But you really got to get rid of the air to the best of your ability. So what I ended up doing here is that I took both ends of the tube and I started going up and down like this. So I grabbed both ends of the tubing and moved them up and down. When you do that, what happens here is that smaller bubbles will coalesce with larger ones. So you want to reduce the number of bubbles. Now, what I did here is that now tape the open end tubing to the wall. That frees up one of your hands. Now take your hand and start tapping on the tubing to force bubbles upwards. And you'll see by doing this process, you'll remove a lot of the bubbles here. So now what you want to do next here, let me make sure I get that, is that then the next step here is that what you want to do here is that you want to insert the stopper into the canister. Okay, you want to insert the stopper into the canister. So let's draw a picture. So if I look at my picture, what you're going to see here is that here's the open end. And if you look at this thing, you're going to, let me make this just a little bit longer. You're going to find that the way I did it is that I ended up doing something like this. And then this guy goes to the stopper. And then here's the canister. So what you're going to find here is that you're going to get this. Here is my dyed water. And then right here, I'm going to put my tape right here. And what I've done now is that I've now contained, I've separated the air and the water so that it looks like this here. So when I look at this thing, the air in the tubing and the air in the canister, that's our constant volume of air. And then this red tape here, this is our marker of the separation between the water. And then, of course, this guy right here is our dyed water. So again, what would I do? I would leave the open end taped to the wall. That frees up your hands. Now you can use two hands to force the stopper in. Now force the stopper into the canister. Now, this is important. Make a good seal. Otherwise, water's going to get into it. And then finally, use tape to mark separation of air and water. So now, let's make the pressure and pressure and temperature measurements. That came out nice. Here we go. So now I'm on step 3. And we want to measure pressure and temperature. In lecture, for an isobaric process, we showed how P was equal to a constant. It was because the piston head was floating. In a constant volume thermometer, it's the water that is floating above the air. So what you are seeing here is that when you look at this, if you look at the tubing, we have a certain amount of water, and then here we have the air. And so what you're seeing here is that now I have two things that are acting. One, I have atmospheric pressure acting on the open end, and at the same time, I have the pressure due to the weight of water, and then the gas pressure of the air has to push up to balance out those pressures. So in other words, the pressure of the gas in this situation has to be the pressure of the atmosphere plus the pressure due to the weight of water. And there's two ways that we can write this. We could either do pressure of the atmosphere plus the weight of the water divided by the area, but that's not the common way that we write it, the way it's written is that it's the density of water times the acceleration due to gravity times the height change. This is the pressure of the gas. This is how we want to measure pressure, where we see that the density of water is 1,000 kilograms per meter cubed. Of course, G is the acceleration due to gravity, and we want to keep the atmospheric pressure in kilopascals, so it's going to be 101 kilopascals. So if I do that, that's how I want to measure the pressure here. So the key to measuring pressure is the height change. That's the key to that thing. So now, how do I set up my measurement process? So what I think I'm going to do here is that I'm going to come all the way up here and I'm going to grab this guy right here. And then I'm going to modify it so that we can actually see what we have here. So here's what we want to do here is that now we want to measure height differences. So let's look up at the setup again. So I'm going to erase a lot of things just to make it a little bit cleaner here. So the first thing that I'm going to do is that I'm going to get rid of almost everything here. Okay, so here's the first thing that you want to do here. So when you look at the setup, here's what we're seeing. One, everything is measured relative to that red tape marker. You need that. Okay. And so what I want you to do here is that it's essential to make sure that you tape this to the wall. In other words, your tape measure should be taped to the wall here. So if I'm looking at this thing, I have to move. So our first measurement's going to be with cold tap water. Okay, that's our first measurement. So what you're going to do here is that you want to adjust the height of the tube, raising it up. Okay, and what I had a piece of tape already at the top of the tube. So I want to raise it till this water is at that volume right there, the red marker right here. Everything has to be measured relative to this. So then if I look at this height change, I'm going to say that that's probably 85 centimeters. I'm going to see here is that my height change is then in this case is going to be 85 centimeters, let's say minus 40. So this is going to be 45 centimeters or 0.45 meters. So here's the thing, as you change the water bath, the temperature, and you have to move it up till you get this at that red marker tape. This is the challenging part here. Okay, so if I go through this process here, you want to then place the metal canister into the water bath. And remember, you want to submerge that canister. So now I'm going to come in with my thermometer and I'm going to wait a little bit to see that this reaches equilibrium. When the temperature stops changing, now adjust the tubing until you can measure this height change. So then what you're going to do here is that you're going to raise the top of the tubing until the water is at the boundary of the red tape. Now, you may not have red tape. The first time I did it with blue painter's tape. That worked for me quite well. You will have to adjust the height for this to happen. You will have to do that. So then, after measuring pressure and temperature, let the canister reach room temperature. So then we have our table now, right? We've already written our table up here. Let me go get the table. Here's my table. In fact, I think I might take all of this here. Right? We now have our table. So then what you're going to go do here is that we want to go analyze this thing. So then what you want to do here is that you want to use Google Sheets or Excel to plot and get a trend line. And when you get that trend line, that means you're going to see an equation that then reads pressure in kilopascals is then going to be the temperature in Celsius, and you're going to get a slope and you're going to have an intercept. And that's what we want. We're after this equation here. So now we want to analyze the data. Here we go. So what you're going to find here is that I'm now going to go and I want to look at this guy. So this is step 4, and I'm going to analyze the data. So here we go. What does the ideal gas say? So the ideal gas law tells me here that the pressure is going to be N divided by the volume of R theory times this guy here. And then I'm going to have plus NV times R theory to 73. But I'm going to be careful here because look what I'm going to do. Here is my slope, my intercept, excuse me. Here is my slope right there. And because we measured in kilopascals, I have to multiply everything times 10 to the 3. This is because we measured in kilopascals. That's why that 10 to the 3 is there. And then this is what I'm saying is my slope and my intercept. This is what you want to get right here. So we want to equate these guys as us. I could tell you that my values were, I had M that was roughly about 0.35, and I had B that was roughly about 92. I went to 3 sig figs. So now calculate these things, okay? So the first thing here is that you want to calculate absolute zero temperature value. So look what I'm going to do. When the pressure is 0, this is going to be the slope. And now look what I'm calling this. This is the absolute value theory plus the intercept. So this immediately tells us that the absolute value in theory should be my intercept divided by my slope. The accepted value the absolute accepted is minus 273 degrees Celsius. Now, if I look at the gas constant, so now let's calculate the gas constant. Our theory, what I'm going to say here is calculate this from the slope. Only. So what I'm doing here is that I'm going to have this guy, which gives me my slope, and of course this is my intercept. So then that tells me that if I look at my M value, this is the slope value. And then this is equal to N divided by the volume times R theory. So then that tells me is that R theory is then going to be the slope divided by the quantity N divided by the volume, where the accepted value is 8.31 joules per mole Kelvin. So it turns out that in this calculation, you need to measure. So you need to measure N over V in your local area. So what that implies here is that you need to, so I looked up my local values in Watsonville, California. And so what I found here is that this is what I found, that the temperature was either, it was either in degrees Celsius or Fahrenheit. It doesn't really matter because you have to convert to Kelvin. And then what I found on the websites, the weather websites, that the pressure was mostly in inches of mercury. So that means you're going to have to convert to pascals. Now, use the ideal gas law to get N over V. So N over V is then going to be pressure divided by RT. And here's what I found here. In my local area, if you plug in my values, so again, in Watsonville, I had my temperature, my local temperature was 23 degrees C. My local pressure turned out to be 30.1 inches of mercury, which I immediately converted to pascals. So when I calculate my value of N over V, I got 1.45 moles per meter cube. That's my value. So now what you want to do here is that use the link in the lab to upload your values into the class Google Sheet. And when you get there, hit the tab that says Lab 1. And what you're going to see here is that you're going to get a table that looks like this here. So here's your table. Now note, this has only 8 values. I truncated it, but in the sheet, it has 45 values. And what you want to do here is that you want to insert your absolute temperature measurement and your gas constant measurement. Remember, I expect them to be rough. So now we need to draw confidence intervals. So then what we're going to do here is that if I have a confidence interval, let's say for absolute temperature, I'm going to have a curve that's going to look something like this here. And then what I'm going to do here is I'm going to set my confidence interval. So what does that mean here? That this here is going to be T minus 2 sigma, T plus 2 sigma. And you could see that this is where I'm getting these two values right here, is that spread. So now, if the absolute prediction that you make falls within the confidence interval, then we say that our predictions are consistent with the accepted value. Ooh, I said theory. I should have said accepted. If it falls, then we say it's consistent. If it falls outside, then we say it's not consistent. In science, we don't calculate percent differences. Then I want to do the exact same thing with the gas law. So if I look at my gas law, I'm going to be looking at this gas constant, and then I'll have, let's say, another distribution curve. And so once again, what am I seeing? I'm seeing here it's going to be r minus 2 sigma, r plus 2 sigma. And once again, does this value land here? So if our value of the accepted value lands outside, then we say it's inconsistent. The values are not so important. It's the process that's most important. Okay. Good luck. Let me know if you have any questions.